To prove the if part, we take an epsilon positive. Then by our assumption, by our previous observation, previously we mentioned that the upper integral and the lower integral lies between the upper sum and the lower sum for any partition P. Okay, remember this result? I will show you. Maybe. Yes, here. We have this result, right? For any partition P, the lower integral and the upper integral lies between the lower sum and the upper sum with respect to the given partition P. Okay? Therefore, the difference of the lower and the upper integral will not greater than the difference of capital U and the capital L. Will not greater than the difference of upper and lower sums. Okay? So using this result, we have this inequality, right? So this is less than epsilon, okay? Because our assumption for the if part is that for any epsilon, you have a partition P, so that this is less than epsilon. But the difference of the upper and the lower integral is always not greater than the difference of the upper and the lower sums. But by assumption, there is a partition P such that this is less than epsilon for any epsilon. So in other words, the difference of the upper and the lower integral is always for any given epsilon. This will not greater. It is always less than epsilon. So let epsilon goes to 0. We obtain that the upper integral will not greater than the lower integral. Okay, but the reverse inequality is automatically true, as we mentioned. So this implies that the upper and the lower integral are equal. Therefore, the function is integrable. So this completed proof of our theorem. Okay. Now we study the theorem we just proved is very important because it is the foundation of our discussion of the integrability in our next lecture. Okay. Now we study the basic property of integration. So the first result is the additivity. Suppose F is bounded, P is a partition of the rectangle I. Then, as we said, P is a partition of I. So our rectangle P will be divided into some sub-rectangle. So this result says that F is integrable over the whole rectangle I if and only if it is integrable over every sub-rectangle. Okay, and also in this case, the integral over the whole rectangle equals the sum of the integrals over all sub-rectangles. So this is the content of this theorem. So F is integrable over I if and only if it is integrable over all sub-rectangle J. And in this case, the integral over I is the sum of the integral over J. Okay. So here we also have if and only if. Therefore, we need to prove both directions. Firstly, we prove the only if part. Suppose F is integrable over I, we will prove that it is integrable over all J. Okay. So suppose F is integrable. So there is a partition denoted by P start of the rectangle I, such that the corresponding upper sum and the lower sum, the difference of the corresponding upper sum and the lower sum is less than epsilon. This is the result of our the theorem we just proved. Okay. So, but we already have a partition P, and now we have this. We by the integrability of F, we have another partition P start. Okay. So, what should we do? Naturally, we take the common refinement of P and P start. So that is P prime, which is the common refinement of P and P start. Okay, then for this P prime, because P prime is a common refinement, because it is a refinement of P and P start, we see that the difference of the lower and upper sum of P prime will not greater than the difference of the upper and the lower sum of P start, and this is less than epsilon. Okay, but this P prime is a partition of our rectangle I, but we want to establish the integrability of F over the every subrectangle. So what to do? Okay, this is not difficult. For every subrectangle J, determined by our given partition P. Okay, the subrectangle for the partition P prime containing in J is a partition of the rectangle J. Okay, this is a result we mentioned. Okay, maybe you forgot this result. I will show you. This is the here. Sorry. Here. Given a subrectangle of the partition P, the refinement, the rectangle from the refinement containing in J is a partition of J. Okay, so using this result, we have the upper sum and the difference of the upper sum and the lower sum, which respect to the partition of J. Of course, in writing this lower sum and the upper sum, we consider F as a function of J, because F is defined over I and J is a subset of I, so we restrict F to J. So this will not greater than the difference of the upper sum and the lower sum of F over all the subrectangle, over all the determined by the partition P prime. Why this is true? Because the lower sum, the difference of the upper sum and the lower sum is the sum of the volume oscillation. Volume oscillation is the oscillation multiplying the how to say, the volume of the small the subrectangles, which is always non-negative. So this this difference UFP prime minus LFP prime is the difference over all the small rectangle, all the subrectangle. Every term is non-negative. Okay, but in the left hand side, you only take the correspond. You only compute the rectangles containing in J, P prime J. Okay, you omit some non-negative term. Okay, so in this picture, you only consider these four rectangle containing in this dash small rectangle. This is J. Okay, but for the right hand side, you compute over all the rectangle, not only these four rectangle inside the dash rectangle, but also other rectangles, and those terms are non-negative. So you increase your summation. Therefore, we have this inequality. Okay. So the right hand side is less than epsilon. So this means that we find a partition of J. Okay. For every J in the original partition P, using the common refinement, we find using the common refinement of our original P and the P star obtained from the integrability of F over the rectangle I, we obtain a partition of our subrectangle J, so that the upper sum, the difference of the upper sum and the lower sum of this partition is less than epsilon. So this implies that f is integrable over the subrectangle G. So this proves the only if part of this theorem. That is, if f is integrable over I, then it is integrable over all the subrectangle determined by the partition P. Okay. Now we prove the if part. So if part means that we know that f is integrable over all G. We want to prove that f is integrable over I. Okay. So given epsilon positive, our assumption is that f is integrable over every subrectangle G. We want to prove that f is integrable over I. Okay. So how to prove this? So because this is integrable, for every G, we can find a partition of PG. Sorry. For every G, we can find a partition of G that is denoted by PG. Here we use the G to indicate that this partition is determined by G. Okay. So that the upper sum, the difference of the upper sum and the lower sum of f with respect to the partition of G denoted by PG is less than epsilon. Okay. So for every G here, here we have 12 subrectangle. For every G we can we have a partition for this subrectangle, so that the lower sum and the difference of the upper and the lower sum is small. So we want to, using the partition of every subrectangle, to construct a partition of the whole rectangle. This is our mission to do this. I said again, using the partition of every subrectangle, we have to construct a partition of the whole rectangle. How to do this? So you have a partition of a rectangle, then you will have a partition of portion of the edge of the original rectangle. Then you take the union of all the partition of the portion. For example, for this, so consider this subrectangle G. Okay, so we have a partition. Suppose it is partitioned into this way. So the partition determines some point, additional point, for the edge of I. Here, this point is I1. Okay, and this is I2 in two-dimensional. If you consider n-dimensional, to every direction you have the corresponding point in the edge of the of I. Okay, so we take the union of every edge. We take the union of every point of the partition of the edge. Okay, so analytically, we write PG in this way. PG is the partition of the rectangle G, and so correspondingly, PG is the Cartesian product of the partition of its edges. So PG1 is the partition of the first edge of G. PG2 is the partition of the second edge of G, and so on. Okay. Then for every PG we write its components. Then we take the union Pi. For example, P1 is the PG1, the union of PG1 for every G. Okay. So in this picture, this picture, so here P1 is the, so for example, this dash small rectangle is a rectangle G from the partition P. Then we the blue segment is a partition, determine a partition. So for this G, we have the partition of the first edge, that is these 3 points. Okay, so for every G we take the union, Therefore, the union is every intersection of the vertical lines in this vertical segment which this edge. Therefore, in this picture, our P1, that is we want this P1 to be the first to be the partition of the first edge of I. Okay, so in this picture, our P1 consists of this point, and this point, and this point, and this point, and also this point, this point, and this point. The dots, the black dot point is the partition of I. Is the P. Our I has a partition P given in the theorem. So the black dot point is the component of P, the first component of P. Okay, that is the partition of the first edge of I determined by our partition P. Okay, and our P1 here is the union. That is not only the black dot point, but also the intersection of these two blue segment, which the lower edge of this rectangle. That is the first edge. Okay, so for every I, we take the union. We take the union. Then